All right, so everyone, welcome. For those of you who don't know me, I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And yes, in my introductions, I always have to get tongue-tied or make a mistake, so got that out of the way. And one of the things I get to do is put together these talks and invite interesting people to come talk to us. And this month, we have Guy Jette. Did I say that right?
Correct.
All right, good.
I don't know about the interesting part, but the name is right.
Okay. All right, good. And he has an MBA and a Master's in Science of Economics. He's worked with the Air Force for 37 years, both active duty and as a civilian. He was selected as a fellow of the American Institute of Astronautics and Aeronautics and Astronautics. Boy, getting my checklist taken care of. And he received the Air Force Outstanding Civilian Career Service Award in 2007. He's now working with Kitt Peak doing outreach, and so he's going to be talking about Kitt Peak and the observatories of southern Arizona. So let's give a warm Maui welcome to our speaker.
Thank you, JD. Appreciate it. It's great being here. All settled here. Okay, so what we're going to talk about this evening, quite a few things, but basically Kitt Peak National Observatory and the observatories of southern Arizona. And we're going to take a little trip. We're going to basically go to Arizona for sure, but we're also going to come back to Hawaii and look at what's going on in Hawaii, how it relates to the observatories in Arizona. And we're also beginning to go into South America. So we're going to go a few different places. We'll start out, I'll give you an overview of Kitt Peak and kind of where it's located and what it's all about. And then we'll go in the history of how it was developed, basically, or how it was founded and why it was founded more than 50 years ago. And after that history, then we'll be talking about how it kind of set the stage for how astronomy was going to be organized in terms of university collaborations and government and university collaborations to this day. So it kind of set the prototype for the last 50 years in terms of astronomy. And then we're also then going to go not only look at specific large telescopes and some of their history, what they've done on Kitt Peak, and relating them back to Hawaii, but we're also going to look at other observatories in southern Arizona. And we're going to look at some other large, what's coming down the pike in the future. And we're going to look at some of the challenges for Kitt Peak, for example. And we're going to tie in a couple of the big issues in astronomy that scientists and astronomers are working on. There's basically three big areas, and we'll be talking about one of those big areas, one of the big unknowns in astronomy that's got a lot of publicity lately. So that's kind of where we're going to go in the next hour. It'll take about an hour, maybe a little bit more than an hour. If you have any questions, please feel free to ask. If you have a long question that takes a long answer at least, I'll hang around afterwards if you have any questions. So any questions to start with? I will ask one question of you folks. How many people have been to Kitt Peak? Oh my gosh. Recently? Well, last year, okay. So then this is going to be old hat, right? It'll be a nice review. Okay, and you folks have been to Kitt Peak also. What about other places like Mount Graham? My gosh, you guys get around. Last year too? That's not easy to get to. It's an all-day excursion to get to Mount Graham. What about Mount Hopkins? What about the Mirror Lab? Okay, Mirror Lab, okay. So we'll see some of that today. And as I was talking to one gentleman here earlier, you can almost plan a weeks-long vacation, an astronomy vacation in southern Arizona. There's so much to do there in terms of visiting the observatories and night observing programs. So we can talk about that too. Now, before we start, though, I don't want you to give me the answer, but I want to let you look at this photograph. Okay, this is a photograph of the McMath Solar Telescope. And we'll talk about that. But what I want you to look at right now, I'm going to ask you a question. Don't answer it now. We will talk about it in about 15 minutes. But the question thinking about, and you may have the answer already, is this sunrise or sunset? So take a look at that. Is that sunrise or sunset? And then we'll come back. I heard someone say sunset. We'll come back to it later, and it'll give you time to work on that and think about what that might be. Okay, first of all, to get our bearings, here's Arizona, southern Arizona. California, Colorado River's over here. New Mexico, here's Phoenix. Tucson's about 120 miles southeast of Phoenix. Kitt Peak. Kitt Peak sits here in what's called the Quinlan Mountains. It's at 6,875 feet, almost 7,000 feet, about 56 miles from Tucson. So you drive west and then you drive south, and there's Kitt Peak. So that's where we're going to be spending quite a bit of our time. But then we're also going to go to the Santa Rita Mountains, which are to the southeast or south-southeast of Tucson. This mountain here is at 9,453 feet, Mount Wrightson. That is not where the MMT telescope is. It was the Harvard Smithsonian Astrophysical Observatory. It's now the University of Arizona and the Smithsonian Astrophysical Observatory. But that sits on Mount Hopkins at about 8,500 feet. We'll visit that location. And then we'll visit Mount Graham. Mount Graham, higher than Haleakalā. Haleakalā is 10,023 feet. Mount Graham is getting pretty close to 11,000 feet, and that's where the Large Binocular Telescope is. So that's a fascinating new telescope that just came on board in the last few years. We'll talk about Mount Graham, and then we will go to Tucson to the Mirror Lab. Some of our folks have already been there, so it'll be a nice review for them. And we won't get a chance really to talk about this too much, but the Catalina Mountains, north of Tucson, at about 9,200 feet, that's where there's a large number of telescopes. The University of Arizona has like 8 telescopes up there at about 9,000. Well, some are 9,000 feet, some are 8,500. So if you're interested, I got some charts afterwards, after we get through, if you want to look at, there's some interesting things about the location. So that's basically where we're going to go in the next hour. Now, so as I said, before we actually look at the history, I kind of want to give you an overview of what Kitt Peak looks like. So this is a view from about the 4,000 foot level. Kitt Peak sits here almost 7,000 feet. This is the large, what's called the male, and when you say this is the male telescope, people say, well, where's the female telescope? No, it's male, M-A-Y-A-L-L. That was one of the directors a number of years ago. And this building is 187 feet tall. But you can see these other observatories along that ridge line. So I just want to give you an idea of what it looks like as you approach Kitt Peak. And you can see this from 50, 60 miles away, this 187-foot building. Now, one reason I showed you this picture, not that I like flowers, but I'm sure some of you folks like flowers, right? The interesting thing about southern Arizona is there's really not 4 seasons, there's 5 seasons. There's the monsoon season. And the monsoon season, here you get some very, very strong lightning storms. This occurs, here's that rolling thunder, from the 15th of June until about the end of September is monsoon season. And the issue here is they don't really schedule any telescope time from, even though it officially begins the 15th of June, never really starts then. It starts in July. So from the middle of July to about the first or second week of September, they don't schedule the telescopes. That's the time when the astronomers maybe can go on vacation, but they can also work on the telescopes. They can take the mirrors out, refinish the mirrors. They can do any kind of maintenance, any kind of test and evaluation. It gives a great break in terms of setting up for the next viewing season or next astronomy session. One thing I kind of miss about Arizona is you don't get thunderstorms. I think I've heard thunder once or twice in Hawaii, and I've seen lightning once or twice. You just don't get the lightning and thunderstorms you get in a mainland, a continental environment. Oh, right. Yeah, that's true. Yeah. 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 Absolutely. Yeah, Tucson gets about 12 inches of rain a year. Kind of like Kihei, right? It's a desert, right? Although it rained last night in Kihei. But Mount Kitt Peak gets 18 inches of rain. And both those locations, about half that rain falls in the wintertime, and half falls during the summer monsoon season. And you're right, the mornings, and you get, once that hits, what happens is the westerly winds turn around to become southeasterly winds, bringing in moisture from the Gulf of California, Sea of Cortez. And once you get that dew point up about 55 degrees, and you can start the day nice and clear, but then the sun comes out, it heats up, and by early afternoon you get these large thunderheads, and it can pour, absolutely pour rain. And I've seen the temperature drop from over 100 degrees to 80 in just a few minutes. Yeah. So that gives you a little background about Arizona. Enough thunder for now. Onward. But it is fantastic. Okay, this is an aerial view looking north, and here's that large 187-foot building that holds that telescope. The next picture I'm going to show you, there's a viewing gallery right about at the 100-foot mark, all the way around, 360 degrees. The next picture was photographed from that viewing gallery. And we'll talk about these foreground telescopes in a little bit. So this is looking the other direction. But you like that? Let's start back here. This mountain here is about 900 feet higher than Kitt Peak. So this is about 7,700 feet. It's called Bobokivari. And it is the most sacred mountain in the Tohono O'odham Indian Nation. And that's the background. That's looking basically due south. Probably, if you look at this far mountain range here, good chance that that's in Mexico, because Mexico's probably about 30, 40 miles from Kitt Peak. Like this telescope here, which we'll see closer, is called the WIYN telescope. W-I-Y-N, and I'll tell you what that means afterwards. But this is the newest telescope on Kitt Peak, and we'll talk about that. This one over here is a 2.1 meter. Been there quite a few years, and we're going to talk quite a bit about that. It has a lot of importance in terms of what we know about astronomy today. Some of the things were discovered using this telescope. And this is interesting. This is called the bug can spray telescope. Looks like a can of bug spray, okay? That has a 2.3 meter reflector that's owned by the University of Arizona. It's called the Bach, which stands for Bart Bach, who was one of the directors of Stewart Observatory. And then these telescopes, this is a 1.8 meter, this is a 0.9 meter, and they're part of Space Watch. So they belong to the university, the Lunar Planetary Lab, and what they do basically is one of those three big things in astronomy. One of them is finding near-Earth asteroids, trying to identify and characterize them to make sure they don't smash. If they're going to smash into us in 50, 60 years, maybe we can do something about it to preclude any problems. So these guys are actually used by the university in that Space Watch activity. This one here is very interesting. It doesn't look very much, but it's called LOTIS, L-O-T-I-S, the Livermore Optical Transient Imaging System. And it's trying to look for optical characteristics for gamma ray bursts. You get a gamma ray burst and trying to identify an optical signature. And then there's a number of other telescopes that we can talk about later. I'll talk afterwards. Ask me about this. This is called the RMT telescope. It looks like a kind of a garage about ready to fall off this trestle. And that's called the RMT telescope, which stands for Rich Man's Telescope. So I'll talk to you later if you want to know what that's all about. There are telescopes you don't see here, which we'll talk about later. There's a couple radio telescopes over here. The solar telescope is here. There's some down in this direction. So there's about 24 telescopes. I mean, not only was Kitt Peak the first national observatory, established in 1958, but it still is the largest number of telescopes in one location. There's like 24 telescopes up here. Even though it doesn't have any more of the very biggest in the world, it still has a large number of optical instruments. So, anyone recognize this? We have some 5 meter, 200 inch. This is Mount Palomar. It sits between San Diego and Palm Springs at about 5,000 feet. It saw first light in 1948. And I show you this because it has an interesting history. It, in fact, was the largest telescope in the world for 45 years. 1948 until 1993, it was the largest telescope in the world. You know what took over in 1993 as being the largest telescope in the world? Going once, going twice? Keck 1. Keck 1 came online and replaced this to be the largest telescope in the world. The reason I show this is after World War II was a big catalyst for science and technology. The nuclear age, electronics, optics, radar, big catalyst. Unfortunately, war has become a big catalyst for technology and science. Everybody's coming back from the war, the GIs, they're all going to college, right? The war's over, go to college. And a lot of them are majoring in science and technology, astronomy, astrophysics. And the astronomers of the day were concerned because they were concerned that there weren't enough telescopes to go around. The demand after World War II was really great, and they had a problem. Unless you were a student affiliated with a major university, like this belonged to Caltech. And Lick Observatory, University of California in Northern California. So unless you belonged to one of those universities, you weren't going to get telescope time. So about 35 astronomers met in 1953 to discuss that issue, figure out what are we going to do about this problem. They met here. Anyone know where that is? Flagstaff. This, you know who this guy is? This gentleman right here? Percival Lowell. Lowell Observatory was established in 1894 at Flagstaff. Who's been to Flagstaff? Great location, especially if you're in Phoenix in the summertime. 110 degrees, you want to go to Flagstaff up in the pine forest. He founded this observatory in 1894, and this is where they met. He was long gone by then, but I just showed you this in terms of the location. So the astronomers met here in 53, And what they decided is their recommendation, and they made it to the National Science Foundation. National Science Foundation had just been founded in 1950 to basically support development of science and technology. Their recommendation to the National Science Foundation was that a national observatory be established somewhere in the southwest part of the U.S. We know why the southwest, right? You want to put it in Seattle. You're never going to use it. You don't want to put it up in the northeast, pollution, clouds. So the southwest has the clear skies, dry air. So the southwest is where they recommended that be put. And their recommendation was that a national observatory that had three large telescopes that would be available to any astronomer or scientist that had a proposal of merit, regardless of his or her affiliation. So they could have been from Podunk University if they were an astronomer or astrophysicist. If they had a good proposal, they basically could get to use a telescope. Matter of fact, it isn't just restricted to astronomers. There were a couple high school students a few years ago, I think there were 2 girls, that they made a proposal to Kitt Peak that was accepted. So here were 2 people, high school kids basically, I won't use the word kids, but high school young adults, that got to work on these telescopes at Kitt Peak. So that is rare. So don't run out and do a proposal. You may not get accepted. Because even now, there's probably every 6 months they review proposals, and they accept 40 to 50%. So you only got about a 40 to 50% possibility. You better have one of the top proposals to get telescope time at Kitt Peak. So anyway, they made that recommendation that a national observatory be established. National Science Foundation said, good idea, go do it, go find a site. So they did a survey of 150 sites between California and Texas. And they went on a little, I understand it's a little Piper Cup, that looks like a good mountain down there. So they narrowed it down to 5, I think 4 of those 5 were in Arizona, then 2, and then they eventually selected, here's his name, they selected Kitt Peak. This was a photograph of Kitt Peak in January of 1959. Now, we haven't gotten to quite the history yet as to why this site and how it got there. But this site was established. At this time, they had started to clear this area right here for the solar telescope. You can see here, this is a 60-foot tower. There's a 16-inch mirror up here. They were, for a year, staring at the North Star, Polaris, to check the clarity of the sky. There was also another mountain near Kingman, Arizona, a little bit higher elevation, that they put one of these 60-foot towers with a 16-inch telescope to check the viewing. And they did select Kitt Peak. So this gives you an idea of what it looked like back then. Now, one of the advantages, why they selected Kitt Peak is a number of reasons. It's very flat up here. A lot of mountains, they'd have to kind of do some earth moving. But Kitt Peak, they had to do a minimal adjustment because it was a flat top in the mountain. It's about, again, 7,000 feet is an ideal site in a lot of ways because you are high enough to be above the dust and any air pollution, which there wasn't probably too much back then, but you're low enough that you're not going to create weather issues. If you go to the 7,000-foot mark on like Mount Lemmon, which is 9,000 feet, or Mount Graham, which is 10,000 feet, you get a lot more precipitation. You get ponderosa pines, huge pine trees, and you get rain. Here, the mountain's not high enough to create weather patterns. You only have that 18 inches of rain gives you pinyon pines and gives you live oaks and oak trees, which go about 15, 20 feet high, and that's about it. The other reason Kitt Peak was selected is Tucson, Arizona, again, about 56 miles away, about an hour and a half, an hour and 15 minutes by car. So you had the infrastructure, even though Tucson wasn't that big. You had the infrastructure for construction companies, so you could build the site. You weren't in the middle of nowhere. And you also had the infrastructure that once you built the site, you have to maintain it. And people have to live somewhere. There are dormitories right now at Kitt Peak for visiting astronomers, but nobody lives there full time. So people can go home at night. Okay, 100 to 100, it's 50 miles, it's an hour and a half at the most. So those are reasons why they selected Kitt Peak. In addition, back then, the Southwest was relatively unpopulated, and light pollution wasn't an issue. So here are the lights of Tucson from Kitt Peak in 1959. Tucson had less than 200,000 people back then. You can see how it's grown. This is 2003, and if you looked at a picture from 2011, 12, it'd be more lights. So even though it's grown, and now there's like almost 900,000 people in the metropolitan area, they have maintained for the last several decades a very strong light pollution ordinance plan and program in Tucson. So they are really stringent about maintaining certain frequencies of light that don't either bother the astronomers or can be filtered out, and they make sure the light is actually is reflected down. It doesn't do any good. You can kind of see here how a lot of this light is going up in the atmosphere. This doesn't hurt the astronomers as much as this stuff up here does. That glow in the air is what hurts the astronomers more than the absolute light. But Tucson's been really good. They do a survey every 10 years. About 18 months ago, they did a survey. They were very pleased that in a 10-year period, there was only minimal light degradation from Tucson. If anything, a bigger issue, you got less than a million people in Tucson, but you got Phoenix twice as far away, but you got 5 million people in Phoenix. And those out of the proverbial barn quite a while ago. How do you maintain a light pollution ordinance program with a megapolis like Phoenix? But Tucson's not so much of an issue. So back then, no problem. Even now, they watch it closely, but it doesn't seem to be affecting the viewing that much. Before they wanted this site, before they could go final, there was one problem they had. Anyone want to guess what their problem was? You get 2 points for this.
Cultural.
Pardon?
Cultural Indian reservation.
Absolutely. Kitt Peak sits right about here on, at the time, called the Papago Indian Reservation. And now they changed their name a few years ago. Now it's the Tohono O'odham Nation. I think Papago was an Anglo name that the settlers gave it, but their own name is Tohono O'odham. So they went to the village elders, the governing council of the Indian Reservation, and they said, hey, we want to build a national observatory on Kitt Peak. What do you think about that? And they said, no. That's our second most sacred mountain. So I gave you guys the hint when I told you that one was the first most sacred mountain. So the second most sacred mountain. So the astronomers scratched their heads and said, okay, what are we going to do? So they brought the elders and the governing council of the Indian Nation to Tucson, where they had a 36-inch telescope at the university. And back in the early 50s, most citizens hadn't looked through telescopes, let alone big ones, let alone Native Americans. And they were showing them the craters of the moon, the moons of Jupiter, the rings of Saturn, and the governing council got together and they decided to use a double negative. It was not inconsistent with their belief system, their culture, their lifestyle to put a national observatory on Kitt Peak. But there were some caveats. Always caveats, right? They wanted no military development on the mountain, no commercial development. So those who've been to Kitt Peak, if you didn't bring food, you were sorry, right? There's a small cafeteria for the people that work there, but visitors, there's no cafeteria. You can buy candy bars. I've had people come up there saying, we didn't have breakfast here this morning. Not really. So there's no commercial development up there, no McDonald's or Burger King. Other caveats, they wanted the power for Kitt Peak to be purchased not from Tucson, but from Sells, Arizona, which is over here on the Indian Reservation. So the power is purchased from the Indian Nation. And when a visitor center was eventually built, which it was a few years later, they wanted to be able to sell their native crafts. They have a number of lovely baskets and Indian jewelry for sale up there. And the other thing is, if there is a position for which a Native American on this reservation is equally qualified with a non-Native American, the Native American will get that position. You don't find too many Native American astronomers, but there are a large number of people on the mountain that aren't astronomers. People ask me how many people, probably 1 out of 6 are astronomers, but you have not only computer specialists, you have maintenance crew, you have craftsmen, you've got technicians, you've got people that work in the cafeteria, you've got admin, so there's a large number of job opportunities that don't involve degrees in astronomy. So that was one of the caveats. The other caveat is any of the tours of Kitt Peak, if you were there, you had to probably pay money for your tours, right, at Kitt Peak? So they get to go on those tours free, which would include the daytime tours as well as the night observing program they have at Kitt Peak. So that was the caveat. And with that, an agreement was signed for, in perpetuity, basically, a lease for the top 200 acres of the mountain in a 2,000-acre peripheral zone. And I think it has an inflation index, but I think it's roughly $20,000 a year. And that basically is how Kitt Peak got founded officially in 1958. Any questions on that before I go on to the next? So, how it works, basically, here's Kitt Peak National Observatory and the sign. It's operated by the Association of Universities for Research in Astronomy under cooperative agreement with the National Science Foundation. The National Science Foundation is the funding agent, and then that money flows to this group. This, again, founded in 1950. Kitt Peak was 58, but in 1957, in anticipation of Kitt Peak, the AURA, called AURA if you want, was founded, which had, so these were the number of universities, but I'll show you a chart that has more, to basically run this national observatory. because the National Science Foundation wasn't going to run it. They needed to establish a group that would. Who better to establish, to run that than an association of astronomers from these various universities? So, this is important because you shall see in a minute, this association started with 1957, these 7 universities. Those are the charter members. And then a couple of years later, Yale, Princeton, in the 70s and 80s, universities joined AURA. In the 1990s, these universities joined. In the 2000s, these universities joined. And if you look at these closely, and these won't be on the test, you don't have to memorize any of these. The test won't include any of this. So right now, I'm not counting the U.S., there are universities here from 6 different countries. You know, Canada, Chile, Germany, Spain, Australia, and Japan, all members of AURA, okay? So where we are now is, and I don't have, this is only the very few charts I have with words on them. National Science Foundation, that's kind of the overarching organization. The AURA, which you talked about, and then under AURA, it has kind of grown because now we have, everyone knows what NSO is. National Solar Observatory. NOAO, and by the way, NOAO wasn't really founded until 1982. I mean, this is 50, this is 57, 82. Because at this point, this National Science Foundation in Aura wanted to get this organization here to manage the number of telescope locations, because there were basically, and you'll see in a minute, basically 3 or 4. Everybody knows what STSCI is? That's Hubble. That's the Space Telescope Science Institute in Baltimore. So that's basically who runs Hubble. And then under Aura, there is, we'll talk about LSST, the Large Synoptic Survey Telescope. We won't talk about James Webb, although I have some charts afterwards. If you want to stay after, we can talk about James Webb Space Telescope. So, Kitt Peak basically has telescopes that belong to NSO, National Solar Observatory. And Kitt Peak has, of course, NOAO, the optical telescopes. Now, I might mention, this is a good place to mention, the NOAO, the telescopes on Kitt Peak that are run by NOAO, not all the telescopes. A lot of those 24 telescopes are run by different. University of Arizona has telescopes, so they're not involved. They're not under NOAO's jurisdiction. NOAO basically has 2.5 telescopes. They have the large 4-meter. They have the 2.1 meter. We're going to talk about those, and they have 40% of the WIYN telescope, which we'll see in a minute. So when we talk about these organizations, they're just the biggies, because in addition to them running those telescopes, they also run the infrastructure for the mountains. So that if you, for example, we have a group called SARA, the Southeastern Astronomy Research Association. There's 10 universities in the southeastern part of the U.S. that have a telescope. There's a Case Western telescope up there. There's telescopes from Michigan and Dartmouth up there. So in addition to the ones that fall under the national jurisdiction and funding thereof, there are private telescopes at these private universities. And then NSO, we'll talk briefly. In addition to Kitt Peak, we'll talk about that telescope at SAC Peak. Everyone know what SAC Peak is? SAC. Anyone been there? Hey, that's good. I'm impressed. Sunspot, 9,000 feet, about 20 miles south of Cloudcroft. Remember what the road, what highway, the name of the highway going to Sunspot, where that National Observatory is? It's Route 6563. Anyone know what you know what 6563 is? That's Anstrom's. That's hydrogen. Hydrogen alpha is 6563. Anstrom's, for those of you that know that kind of thing. Or 6656 nanometers, right? It's kind of interesting that the name of the highway, they had that highway. Yeah. Not many people probably get that to go there. Okay, so SAC Peak, I got a cool picture. I don't have it in the primary because I want to be out of here in an hour, but I've got a backup that shows a beautiful shot of that location. The Haleakalā, where they have just broken ground. It was approved in November. It's just broken ground for the Advanced Technology Solar Telescope, which we'll talk about. That wasn't loud enough. Back for the back. Which we'll talk about in a little bit, okay? So then NOAO, the reason they had to put NOAO together to run, because there was too much for AURA, or National Science Foundation, with the Kitt Peak telescopes. Mauna Kea, there's one of the telescopes on Mauna Kea, which we'll talk about in a minute. The Gemini telescope belongs to NOAO. Chile, at Cerro Tololo, has a Telescope and Sierra Pachón. Pachón has the Gemini, which we'll see in a minute, and Tololo has another telescope which we'll see, what happens to be a sister of the 4-meter on Kitt Peak. Okay, this happens to be the headquarters of the National Optical Astronomy Observatory as well as the National Solar Observatory in Tucson. And it's at the campus, it's right across the street from the campus, but it's not really on campus, but it's right close. Matter of fact, this picture was taken from the steps in front of the Stewart Observatory, which is part of the University of Arizona. I might mention a note right here, when Haleakalā Telescope gets built, they're going to move the headquarters for the National Solar Observatory sometime in the next few years, maybe not until they finish, but it's going to move to Boulder, Colorado, so it won't even be in Tucson. So this is Mauna Kea, that large 8.1 meter Gemini, and this is Pachón. It sits down there at about 8,775 feet, and these are about 1990. I think these came online for first light. So the Gemini twins, and the beauty about this is one covers the northern hemisphere, one covers the southern hemisphere. They have complete sky coverage. And here's a picture of it. And here, another question for you guys. Most telescopes are coated with aluminum, right? They coat those with a very thin layer of aluminum. These are coated, everyone recognize what element that is? Silver. Ag is silver. And all the mirrors in these two telescopes are covered with silver because silver has a better reflectivity, unless you get into the ultraviolet, then it doesn't. But basically, for anything that's about 400 nanometers or longer, into the 800 where you have your red, then this is very effective material to cover. It has better thermal infrared emission too. It's very much efficient. It's more expensive and it's harder to basically apply, but these are the only large silver mirrors of any large telescope in the world. Okay, now you get a chance to go back to this picture, okay, the introductory picture. This is the McMath Solar Telescope, but the question is this sunrise or sunset? Who thinks it's sunset? Who thinks it's sunrise?
I think it's cheating.
It's which?
I think it's
Cheating?
cheating.
So, young lady, why do you think it's sunset? You said sunrise or sunset? You said sunrise, didn't you? Who said sunrise? Why do you think it's sunrise?
Because the clouds are all white.
Oh, well, it's a little bit tricky because this must have been a multiple exposure, because you're not going to have the sun setting or rising and have these shadows coming down here. Okay, so it's a little bit tricky. Okay, so let me give you a little hint. Well, what do you think this has to do with anything?
Latitude.
Okay.
Polaris.
What is the angle? Anyone going to guess what it looks like? Most people look at it in person and say 45 degrees.
No, it's not what it's less.
Okay, the latitude of Tucson is 32 degrees. And this is 32 degrees. And this basically points to the North Celestial Pole. North Celestial Pole, if you're at 32 degrees latitude, the North Celestial Pole, where Polaris is almost, it's not exactly on that spot, but that is 32 degrees above the horizon. Just like right here, we're roughly at 20 degrees, 22, 21. We'll average that and say 20. 20.7. So if you go out tonight and look 20.7 to the north, if it's clear, you're going to see Polaris. Okay, so if you're at 45 degrees somewhere in Seattle and look for Polaris, it's 45 degrees. Okay, so this is basically a tortoise mount telescope, albeit one that's a little bit unconventional because you don't see them quite. I don't think I've ever seen a building anywhere in the world like this. But if this is pointing to the north, then that's got to be east, right? If you look at it long enough, it really should dawn on you. It should dawn on you quicker than that comment did, right? So this is looking east. Now, and I'll mention, and you'll see it again. Everybody knows that the sun rises east and goes across the sky and sets in the west, right? Stars rise in the east and set in the west, right? Do they really? Yeah. The planet rotates west to east. That was a trick question, right? The planet rotates west to east, and in that rotation west to east, it seems like the sun is rising because it's the Earth is rotating. So the idea here is these mirrors up here, and we'll talk about those in a second, can pick up the sun in the morning, for example, and just on that one axis, equatorial axis, they can just twist around, they can follow the sun across the sky. Or for that matter, they use this telescope for bright stars and bright planets. They do planetary studies with this as well, and stars. So they can use it in the daytime. Might point out while we're here, back here, this is called SOLAS, which is Synoptic Optical Long-Term Investigations of the Sun. So it's another solar telescope looking at magnetic fields and magnetic strength that's in this building right here. Okay, and here is you really get a feel for it here. You can see these star trails as the Earth rotates, and you can see that these are apparently rotating around a common center, which is way up here. That this points to. Okay, interesting photograph. This was taken in 1992. It's an 8-hour exposure, and if you recall, in 1991 there was a volcano in the Philippines called Pinatubo that blew up, and it threw a lot of dust and debris in the atmosphere, and we had great sunsets for about a year and a half. So this gentleman, Bill Livingston, he took this photograph and time exposure, and this was that, and there's no filters here, this was the glow he got off of that side of that structure over a 9-hour period, including when he got the star trails. They say that, I can't really tell, but they say that these are to be the belt stars. I think the belt stars of Orion are here, which makes sense because for the astronomers, you know, the belt stars of Orion, they rise due east. Okay, so I don't know which one is it, you know, offhand? But this is basically, so that makes sense. That's where the sun was. This is where, in fact, if you're lost and you can't find the North Star, if Orion's out, especially if he's low in the horizon, east or west, you can tell that's the direction. It's a way to find your way home in the dark if Orion is up. Bill Livingston, I'll talk about him briefly. This gentleman was an astronomer. He's worked for over 50 years at Kitt Peak. He's in his mid-80s. He still works there. He's retired. He still works there as a volunteer. I think his wife just says, "Get out of the house. Go ahead." So he goes to Kitt Peak several times a week. He stays over a few days. He still works up there, and he took some of these great photographs. This was like 20-plus years ago. Okay, now let's talk a little bit about the telescope. 100 feet high, right here, 200-foot diagonal, and then it goes another 300 feet in the ground. So 500 feet, and you'll see that in a second. On top of this, there's a 2-meter, although the next chart says 2.1-meter heliostat, which is a flat mirror, which picks that sun up. There's also 2.9-meter mirrors, so it's really a 3-in-1 telescope. They can actually be doing 3 different experiments or observations with this telescope. If you go there, those that have been there, you probably realize if you walk this way and go around this corner right here, there's an observation room. You can step inside, you can look up the shaft and down the shaft. You can also walk around and go in and look at the viewing area through this door right here. But interesting, this is made of copper. And what they have to do, I just explained this first, they have to cool this. There is 5 miles, 25,000 feet of tubing, of lines in here, which they pipe chilled water, because in the summertime, this gets too hot and they have to chill it down to be the same ambient temperature as the outside, whether it's daytime or night. And in the wintertime, this gets too hot below ground, and they've got to chill below ground. So they chill below ground, cool down in the winter, above ground in the summer. And the reason they have copper panels is copper really helps to conduct the heat into those pipes so that the chilled water mixture can remove the heat. This white paint, everybody wore sunblock this morning? Chances are it had titanium dioxide. When you go home, check. Titanium dioxide. The paint is made of titanium dioxide for the same reason your sunblock has titanium dioxide, because it reflects the heat, reflects the ultraviolet even. Here it is. Here you can see the tunnel. And what makes this by the way, as soon as they established the observatory, 1958, they broke ground on this. I showed you that flat area on top of the mountain. It saw first light in 1962, so it was operational in 1962. It has been the largest solar telescope in the world for almost 50 years. Didn't quite make it because in 2011, the New Jersey Institute of Technology, they came up with a 1.6-meter mirror in Big Bear, California. So this is now tied in terms of size of the mirror. We say largest telescope. It's still probably the largest, being 500 feet long. But what defines a telescope size is the size of the mirror. So the image-forming mirror, way down at the end of this tunnel, 1.6 meters. So that's what made it the largest telescope. So the idea is the sun is picked up, reflect down this 500-foot tunnel, concave mirror forms an image, reflects back to a trolley system, which can be moved back and forth here, project the image down into several instruments in the observation room. And you can see here there's some spectrographs that go quite a few meters into the ground. Very long, large spectrographs.
So does everything move remote?
No, they have people working. They have people working there. I mean, I don't think it can be remote. There is some telescopes that can be remotely controlled, but this isn't one of them. Oh yeah. Well, the way they enter is go back to the previous one, right down here. I mean, you can enter here, but you have to climb up this. They have a series of steps that you don't have any handrails or guardrails. You wouldn't want to walk up those steps. But yeah, they would enter right in here into the observation rooms, and it also includes the observation rooms for this telescope here. If you ever go to Kitt Peak, make sure you don't forget to go both this location and the location down here. Okay, any questions about that at all?
Well, why, I see it has a vacuum spectrograph. Why would that part be in vacuum and not the whole optical train?
This optical train here?
Yeah, I see that it says a 15.5 meter vertical vacuum spectrograph.
Yeah. So you're saying why wouldn't this train be?
Yeah, why just do that part of it instead of the whole thing?
Well, I think back then, I don't know if we had the technology in the 60s to make this whole thing. I think that the Dunn telescope, its sunspot, I think that has a vacuum.
Yes, it is.
It's a vacuum. I know it actually floats, and that telescope is 130 feet off the ground. It goes into the ground 230 feet, and it floats on a pool of mercury, and that is vacuum. But see, the Dunn came after this, so it's a little more modern, although it's smaller than this. Yeah.
The reason why I brought that up is if part of the path is in air, then the value of just that extra 15 meters or so of vacuum is
Yeah.
very much.
Yeah. That's a good question. Okay, so anything else I should tell you about this? Probably not. We need to probably move on. Now, this is, I have my spectroscopy expert there. So this is a spectrum of the sun, okay? And the beauty about this is, yeah, just like a rainbow, just like it's like a prism effect, the refraction of the light. The spectrograph takes the light of the sun and breaks it into the colors. Everybody remembers Roy G. Biv from high school physics? Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv is important all these years later, right?
Or
The other way around, yeah. So these dark areas here, these are called absorption lines. And the beauty about absorption lines is this is how astronomers can tell what's in the atmosphere of the sun. Okay, what is between us and that light? Because every molecule absorbs different frequencies of light. And these are fingerprints. So the astronomers would basically read this and tell you a lot of information. And they can tell you what elements, what the chemical composition is, even things like mass, density, temperature, size, luminosity, magnetic field characteristics, velocities, radial. Is that object coming to or towards us or going away? Or transverse. What's the velocity? Or rotational velocity. Most of what we know about stars and the sun and galaxies comes from spectroscopy, studying the spectrum of stars. And take a good look at this. Take a look at it, because it'll be coming up in a minute. Now, everyone knows what this is, right? We're on home turf. Pan-stars. Now we're on Hawaii. This is a great photograph. Pan-stars. Everyone knows what pan-stars stand for? Panoramic Survey Telescope and Rapid Response System. Pan-stars. It's a 1.8 meter. And the beauty about pan-stars is it has the largest camera in the world. And I know some of you know that already. 1.4 gigapixels. Big, powerful mirror, even though I think it's about 40 centimeters by 40 centimeters. And this is involved. It's on the mountain right now. And for those of you who don't know, the operation room is right down the hall. Upstairs down the hall is where they operate pan-stars. Do I have any people that work in pan-stars? I know that Steph works on pan-stars. He's proud of his child, right? So this telescope, basically what's it doing? About every week, 4 times a month, it does a complete survey of the sky that it can see. And what it's looking for, and we're doing a lot of survey telescopes, you'll see some more, it's looking for changes. So it takes a complete picture of the sky, And then a week later, it takes another complete picture of the sky, and it does that continuously every week. It's looking for changes. Is there a near-Earth asteroid that popped in there? Is something that we need to worry about? Do we need to characterize the orbit that's going to hit the Earth eventually? Or a supernova? Does it see a supernova that it then can alert the astronomy community so they can look at it rapidly and try to find out more about that supernova? Or is there a comet? And recently I read that there was a comet that Pan-STARRS found that's called Comet Pan-STARRS. And it should be quite bright this year, 2013. You're hoping it could be very, very visible this year.
March the 1st.
March the 1st? So the neat thing about not only the largest camera in the world, but this is Pan-STARRS 1. Pan-STARRS 4 coming along, a little bit of luck, keep your fingers crossed on any of these things because of the cost and the schedule and all. Pan-STARRS 4 will have 4 of these 1.8 meter mirrors with 4 of these 1.4 gigapixel cameras. I don't know whether that's going to be in Haleakalā or Mauna Kea. You know, Steph, where it's going to go?
It should be Mauna Kea is where they're looking for.
Mauna Kea? Okay. So Pan-STARRS 4 would go there. But this is a really cool instrument on Mauna Kea. And we all know where this is. I'm sorry, Haleakalā. We all know where this is, right? This is our favorite mountain, Haleakalā. And here you can see, here's the Pan-STARRS 1 right here. Here's Air Force 3.67 meter telescope. This is EOS, which is Advanced Electro-Optical System. Air Force uses it to image satellites for space surveillance. And you can also see they have another instrument here, GEODES, which stands for Ground Electro-Optical Deep Sky Survey. I think that's, if I got that right. And that's why the Air Force has several of these telescopes around the world. So this is the site, and this is where, this is right there right now, but this is the Advanced Solar Telescope, where they were thinking, at least when they did this drawing, of where they were going to put that telescope. Pardon? I think it's off to the side. But this is in the way. You guys should told me. Okay, I think Falks is over here.
No.
Other side? Is it behind it here or behind it over here? Okay, it's blocked. Yeah, sorry.
Where's the new solar one going to go?
I think it's going to go right here.
That's it. That's the rendition.
Unless they now again they just broke ground on it in the last month or so because they get final approval in November. And I got another picture here of it too. So here it is here, the rendition. This is about 145 feet high. So you'll be able to see it. It's going to be quite large. It's not quite as high as that one on Kitt Peak that was 187, but still going to be 145 feet high. About $400 million, but fortunately nobody can afford these. Everyone's got to chip in. The Air Force is big on this. They're paying for part of it. I understand Bill Gates threw in $10 million, and Paul Allen threw in $20 million. And China's interested. So different countries, and there's a number of different organizations, universities, and nations that are interested in all these big telescopes, including this one. Because if you pay money to help build it, then you get to use it and or get the information from it. And I know China is really interested in getting into astronomy. Yeah. So more and more we're seeing China's names on charts like this. Now, what makes this telescope, this will become the largest telescope in the world. And as a matter of fact, they're thinking of decommissioning the one on Kitt Peak even before this comes online. Although what will probably happen is it doesn't cost much to run the solar telescope on Kitt Peak, about $200,000 a year. So they'll probably get a university or two to basically, for a couple $100,000, they can basically, they're not going to, the National Science Foundation won't sell it to them. They'll just say, you take it over and just run it. So I think that they're going to find some takers for the telescope on Kitt Peak. But the national, the country can't afford it. The National Science Foundation, NSO, they can't afford to run Kitt Peak, SAC Peak, and the ATST. It's kind of a budgetary issue. This is the mirror. It was cast in Germany. It's shot. As a matter of fact, I saw it. It was sitting outside of the NOAO headquarters in Tucson on a flatbed in a big old crate. It said shot. That's from Germany. And they are basically polishing it at the university, at the Optical Sciences department at the University of Arizona. Now, we talked about, we saw the spectrum of the sun. This is a great place this is Hawaii. This is Maui. This is a rainbow. That's pretty obvious. I shouldn't have said that, right? Talk about the obvious. But what I think is interesting is, Hawaii is a place of rainbows, right? And guess what? The telescopes they're about rainbows. So there's a rainbow connection. I almost felt like, no, that wasn't supposed to be a pun. I thought about getting Kermit the Frog, singing the Rainbow Connection here, but I figured that would be too corny to have Kermit the Frog singing the Rainbow Connection. So, I think that if you think about, I know there's been some issues with the native culture about putting this big telescope on Haleakalā, but if you think about that rainbow connection, these are rainbows. This is a rainbow. And that's not the only connection with the rainbows and with the spectrum. This happens to be the spectrum. This is a little bit different than the sun. If you were to put this next to the solar spectrum, you'd see these absorption lines were different because this is a different star than the sun. This is Arcturus. So it has a different absorption pattern. Some of the same elements are in Arcturus, but there's some different ones. So the thing about Arcturus is considered to be the zenith star of Hawaii. That the Polynesians, when they came, up from the Marquesas and from Tahiti, they looked, at least in the summer solstice, Arcturus is directly overhead, at least over the island of Hawaii. So it was a star they used to navigate by. So matter of fact, if you go out, you're not going to see it now, but after the spring equinox and before the fall equinox, you're going to see Arcturus, and again, summer, it's going to be right overhead. So all you got to do if you find Arcturus is, here's the Big Dipper, and you've heard the story here, the handle, you arc to Arcturus, right? So that is a key star in the Hawaiian history, so key that this voyaging canoe, the Haleakalā, did I pronounce that correctly? That basically is Hawaiian for Arcturus. They named that star Arcturus. Is my understanding. It's also called the Star of Joy. So this has been around since the mid-1970s, transiting across the Pacific using ancient Hawaiian navigational techniques which use the stars. And what are we about on Haleakalā? We're about stars. It all fits together. If I was native Hawaiian, I'd be proud to have those star viewing telescopes on my mountain that my ancestors used to get to Hawaii. And the rainbows and the spectrum. Anyway. So, now we're going to change a little bit. VLBA. I know some of you know what that means, right? Very long baseline array. There is 10 radio telescopes. This is the one on Kitt Peak, 25 meters in diameter. So it's almost 80 feet in diameter. And these 10 radio telescopes stretch from Mauna Kea, here's the Hawaiian connection, all the way to the Virgin Islands, St. Croix. 5,000 miles. These radio telescopes act like interferometry. They act together. It's almost like having a large telescope, and to some degree, it's almost like having a telescope 5,000 miles in diameter. The other thing is it's so accurate, they can tell if there's any shifting in the Earth, they can tell the distance between those telescopes over that 5,000-mile span of 1/5 of an inch, 5 millimeters. They can tell if there's been movement in those telescopes 5 millimeters. Incredible. And just want to point this out. Everyone been there? You guys have been all over, huh? This is the very large array, VLA, that's in about 60 miles west of Socorro, New Mexico. These are 25-meter telescopes. There's about 27 of them. They can be adjusted along these tracks. And I want to show this to show you this is not the VLBA. This is different. Even though one of the VLBA telescopes is nearby. Okay, I want to show this real quick. These are the institutions using the NOAO instruments on Kitt Peak. And these are the ones that, the 4-meter, these are the various groups that are using the 4-meter during the month of January. A lot of different universities. And again, most viewing, yes?
The array that you just showed that was like a Y, was there a purpose in putting it in a Y fashion and putting so many together?
The data reduction for the interferometry symbol.
I mean, I guess they could. Well, it's simple in terms of you put them on a track and you can move back and forth, make it larger or smaller. You could have put it. Some of those large array telescopes now are being like in a field, kind of sporadically. But this is, I think, cheaper in terms of cost to line them up like that, and you can spread them out. More efficient. Okay. Yeah. So most viewing runs in these telescopes are 3 to 4 to 5 nights. So any one night, there may be a combination of 2 or 3 or 4 or 5 of these different universities working on a similar project. And here, basically, these are the ones that are using the WIYN telescope, which we haven't even talked about yet, and these are the ones that are using the 2.1 telescope. 38, I'm going to go back, 38 different institutions. Oops. 38 institutions, 9 nations. If you look at, between Korea, Canada, there's 5 different nations involved. Okay, we're going to talk about the 2.1 meter telescope. This has been around, first light 1964. You can see here an old equatorial mount, so very heavy and bulky. And this axis here, if you were to draw a line, this points to the North Celestial Pole right through here. And this was the way they built telescopes back here in 1964. Everyone know who's this? Does everyone know who this lady is? No, it's not Margaret Geller. It's Vera Rubin. She is a young astronomer, and by the way, she's still a practicing astronomer in her mid-80s, works for Carnegie Institute. She was basically using the 2.1 meter, late 60s, early 70s, to study galaxy rotation curves. And to kind of explain what that is this is a solar system rotation curve. Okay, we all know that 99.8% of the mass of the solar system is in the sun. And what happens then is the further out you get from the sun, the slower the planets move. So you got Mercury here, and this is kilometers per second. Mercury is moving at 48 kilometers per second. And then you have Venus, and Earth is 30 kilometers, and so on down. This is Jupiter. By the time you get out to Pluto, you're only moving off 5 kilometers per second because the gravitational pull is a lot less at Pluto at 40 astronomical units. That's 40 times the distance between the Earth and the sun. So the further out you get, it drops off drastically. The velocity drops off according to the square root of the radius. So what Vera was doing, she was looking at galaxies. And if you look at the matter in this galaxy, what you see here, you would think, if you start measuring, you'd think the stuff that's going around this part is going to be going much faster. By the time you get out here, the outer part of the galaxy, these stars and clusters and gas is going to be going much slower. So what you would anticipate is that the galaxy rotation curve, the velocity would drop off as you get away from the galactic center. But what she observed were the galaxy rotation curves were flat. Basically flat, which was a puzzle, because there's not enough matter that you can see that would cause these to be flat. Yes? This one the one I showed you would be tough because it's face on. But what she was looking at galaxies that were angled, and at the time they had a really powerful spectrograph, which could tell whether the edges of that galaxy were coming towards or going away, and the velocity.
That's how they find the planets.
Yeah. So it was basically back to spectroscopy can measure those velocities through redshift. Is it going away or is it coming towards you? Yeah. I mean, it all boils down to spectroscopy. Okay, so based upon what she then came up with, the astronomy community finally got the idea that, hey, there's something out there. The easiest way to explain this is there's matter that we can't see that is gravitationally influencing all the stars and the speeds, but we don't see it. So if we don't see it, we call it dark. Dark matter means we don't know matter. We don't know what it is. That's the whole genesis of dark matter. But she really wasn't the first. This guy here, everyone here recognize him? Well, she was doing this in late 60s and early 70s.
So she actually concluded there was dark matter.
And in 1975, she did a seminal paper on dark matter in one of the prestigious. So it was kind of accepted back in the mid to later 70s. Yeah. Now this guy here is probably your weird Uncle Harry, right? This individual, his name was Fritz Zwicky. And I understand he was kind of a crusty old guy. He kind of looks crusty, at least in this photograph. He was a Swiss astronomer that worked for Caltech. And back in 1933, he was looking at clusters of galaxies in their rotation. And he happened to be looking at this galaxy cluster. This is the Coma cluster. About 1,000 large galaxies in here, maybe several tens of thousands of smaller ones. And he looked at this and looked at the rotation and said, there's enough matter there, these things should be flying apart. And he said, there's a lot of missing stuff here. But he was kind of, at the time, they kind of discounted him because he was, this. when Vera came along, they really nailed it down with the gravity rotation curves. But even now, there's more than just gravity rotation curves. Now we have other ways to look at dark matter through gravitational lensing. Okay, these are a couple galaxy clusters that have passed through each other, and through what's called weak lensing, they can basically tell this blue here is supposed to be the dark matter. This red is just some gas, intergalactic gas that kind of got electromagnetically attached. So that's why as these pass through each other, this will stay behind. But they can tell here that there's more mass than is indicated by the light that they see. And they also can tell because there's some items in the background, just like these lenses here, swats in the background that are being distorted by that dark matter, by that gravitational field. Not only been distorted by dark matter, but actually distorted by the visible too. This is called a galaxy Einstein ring. And this galaxy is for sure, and this dark matter is this is a galaxy that's in the background that happens to be distorted in the shape of a ring. So by using gravitational lensing, both weak and strong, they figured that's another way they figure out, and they've kind of looked at there's matter there that we don't, that interacts gravitationally, but that's all. Here's an example of Milky Way or any galaxy, and they're saying there's got to be this dark matter halo around basically all galaxies. So of the matter that we know about, light matter and dark matter, 15% is visible. 2% planets and stars, 13% intergalactic gas, but 85% of the matter that we at least think we know about is dark matter. Okay, but this is only half of the issue. We'll talk about the other half of the issue in a second. Okay, real quick, I tell you, it's been can you believe it's been an hour? I've only been up here 15 minutes. Einstein had that theory of relativity, right? When you're up, everything's relative, including when I'm up here. It seems an hour seems like 15 minutes, and when you're sitting out there, an hour seems like 4 hours. So if anyone wants to leave, that's fine. I mean, you might have places to go, things to do, movies to watch. So feel free to walk. Feel free to take off. If everybody okay? Okay, we'll keep going. This is kind of an interesting dome. The shape here it's called the WIYN telescope. And what the WIYN stands for is the universities of Wisconsin, Indiana, and Yale. Those three universities each have 20% of this, 20% of telescope time. And N stands for NOAO, the National Optical Astronomy Observatory. And they have 40% of the telescope. The telescope is quite unique. 1994, it saw first light. Unlike the other telescopes on Kitt Peak that are equatorial mounts, this is the newer mount called the altitude azimuth. This telescope, instead of being hanging on this big support structure, a diagonal, so it can follow the north celestial pole, this is basically a simple telescope that moves up and down. That's the altitude, azimuth, sideways. And even though the star trails curve across the sky, with computers, this kind of motion can easily be adjusted to follow things across the sky. So it's a lot cheaper because we talked about, we'll look at it a little closer, that large 4-meter telescope is only a little bit bigger than this. But that 4-meter telescope, you're going to see the mirror weighs 15 tons, 30,000 pounds. This mirror only weighs 4,000 pounds. So it only weighs 12% of the mirror that's only a little bit larger. And the building itself is much smaller. Everything is lighter, compactor, which makes it cheaper. And the fact that computers make this, even though computers cost more than the computers we used to have, they're a lot cheaper than massive domes and construction. Okay, I wasn't supposed to quite show you that yet. Okay, a few years ago, the head of the Yale astronomy department was at the WIYN telescope, and he was in the room there where they had the computers, and he was falling asleep. He opened up his eyes, and he saw these two eyes staring at him. So he was kind of shocked. And it was one of these. You know what this is? A ring-tailed cat. A ring-tailed cat. So this guy was living in the observatory, and they called him Dave because there was a lot of astronomers who had the name Dave. So they thought that was a good name. And they let him be there about a year until they found him. There was toe prints on the telescope lens, and they could kind of clean those off. And once they found mouse parts, dead mouse parts, it was time to basically relocate Dave. So they got rid of Dave. The outreach program is pretty strong at Kitt Peak. They have a night program, observing program. You can stay till about 10 o'clock. They have an advanced observing program. You can stay all night long. This is a small telescope. It's about a 4-inch. It's a solar telescope. And we have docents in here that basically hang around, and the visitors walk in, look at the sun. They have an H-alpha calcium. So we had a docent that was sitting there one day, and there was nobody around, no guests, so he was playing his native flute as he was sitting in here all by himself. Guess what shows up? Worse than Dave, a western diamondback rattlesnake. And I guess it kind of cornered him. But fortunately, they all carry walkie-talkies, so he called and people came and they relocated him to the place where Dave was relocated. One thing nice about hiking in Hawaii, you haven't got to watch where you put your hands or your feet. There aren't going to be any rattlesnakes, okay, unlike Arizona. There are scorpions. So this is the 4 meter.
Centipedes.
And centipedes. Oh, yeah, I've seen centipedes that big.
Like their age is the devil, don't they?
Oh, wow. This construction began like in 1968, saw first light in 1973. And this is a 93-foot pier in here, 33 feet in diameter, 18-inch walls, basically. And this is the pier that the telescope is connected to. The foundation is into the earth. Because when the wind blows, when this thing vibrates, or when they move the dome, which weighs 500 tons, and it vibrates, the telescope is rock steady, okay? And you can get an idea of the scale here. You can see this truck. And here it is completed. The observation deck is right here. One thing I want to mention, when this was built, this telescope, or this, not the dome, but the telescope specifically, which you'll see here, in 1973, 25 years after Palomar, it was the second largest telescope, 4 meters, second largest in the world. Anyone want to guess where it is right now? Where it ranks? 10th? It's tied for 25th. It's tied for the 25th biggest telescope. That's how many big telescopes there are. And I say tied because when they put this in Kitt Peak a year or two later, this is called the Blanco telescope that's in Chile. It's Sierra Tololo. It's 7,200 feet. And it's kind of the identical, it's the twin. And it has a significance you'll see in a second. When this was put in like 1976 in South America, it was the largest telescope in South America, remained that way until 1998, so about 22 years. I wanted to really quick show you, I won't go through these, but for January 2013, these are the 7 projects that they're working on. So each one of these is going to be an observing run of 3 to 4 to 5 nights. So there's things that range from T-Tauri stars, which are basically new stars being born that haven't quite reached nuclear fusion yet, galaxy groups, Z5 quasar candidates, Z5 redshift distance that puts them out about 12 billion light years in terms of when that light left that quasar, supernova. So some of the things that their projects they're working on this very month. Anyone know who this guy is? Hubble, named the space telescope after Edwin Hubble. And this was the 100-inch. Hubble went to Mount Wilson, right outside of LA, in about 1919, and this telescope, the 100-inch Hooker telescope, saw first light in 1918. It was the largest telescope in the world for 30 years until Palomar. So what Hubble did, back then in the early 20s, the astronomy community, they were not quite sure. They looked at these spiral nebula in the sky, like they called it the Andromeda Nebula. And they couldn't quite figure out. Some astronomers thought that was just gas in our, a nebula of gas in our galaxy. Others astronomers said, no, that's another island universe. So there's a big argument back in the 20s. Well, he was looking at cepheid variables. Cepheid variables had been worked on a few years earlier. They helped to figure out the distance because they have a constant, basically, if you can see the brightness of a cepheid and you compare it to how it varies in brightness, you can figure out how far away it is. Using those, he's the first guy that basically proved that these spiral galaxies, these spiral nebulae, were not in the Milky Way, but were other galaxies further away. That happened in the early 20s. And that was kind of all taken care of by 1925. In addition, in the late 20s, he's the first one to figure it out, although they talked about it, but using redshift, using basically the fact that, the Doppler effect, it's like a sirening of a car. So as light recedes from you, those wavelengths are stretched to the lower wavelength, lower frequency, and as they come towards you, those light waves would become bluer because they become more, the frequency would increase and the wavelength would decrease. He's the first one to figure out, using redshift, that the further out we look at galaxies, the faster they're receding from us. It was called the Hubble constant. And that is instrumental because we've known since the 1920s that the universe is expanding. As a matter of fact, we're talking about redshift. That's pretty good. You guys got that. You got this quicker than you got the one about the finally dawned on you. No, this is actually a bumper sticker. I took the picture of this. This is a car parked at the NOAO parking lot. And again, the idea is, you know, redshift says that if something's going away from you, it's going to look red. So if this looks blue, you're going too fast. You're doing a blue shift, okay? And if you don't get that, talk to me afterwards and we can talk about it some more. Okay, anyone know who these people are? Going once? What was that? Okay. We have known since the 20s that the universe is expanding. They were trying to figure out in the 1990s, and there was two teams trying to figure out, okay, we know it's expanding, but is there enough matter, dark and otherwise, that eventually it's going to slow down and the Big Bang is going to come into a big crunch, or is it just going to kind of go on forever and just everything is going to disappear? So two teams independently were looking at this. Both of them were startled independently when they figured out, looking at supernova, type 1a supernova, they figured, to their shock, they knew that the universe not only is expanding, it's accelerating. And they don't know why. And even now, this was basically 1998. They got the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through looking at this supernova. And it's still a big puzzle. We don't know why the universe, I should say, why it's accelerating. So right now, the state of cosmology is, we know what 4% of the universe is. What we see in gas and stars is 4%. 23% is dark matter. And then 73% is dark energy. So the energy density of the universe, we don't know what 96% of it is. Yeah, and if you look at energy and matter are kind of the same. Remember Einstein? E equals mc squared. Energy equals mass times the speed of light squared. So energy and mass are kind of the same, and matter are kind of the same thing. So that's one of the big puzzles of astronomy is dark matter, dark energy. Big, big issue. As well as the other big issue, of course, is extrasolar planets. We're interested in that. And then for a survival point of view, we're interested in near-Earth asteroids. So where are we going from here? This is the Blanco telescope. And you see right here, they have just installed on this 4-meter that's down in Sierra Tololo, the DCAM, dark energy camera. 4-ton camera, including all the filters and all, on this telescope. And it's going to be pretty large, not quite like the one on Haleakalā, but I hear that this is the most sensitive, powerful telescope. Maybe it's because it really looks far into the infrared. Almost 600 megapixels with a 2.2-degree field of view. And it's going to be a survey. And it's basically 100-plus scientists, 23 institutions, a number of countries, of course funded by DOE, Department of Energy, because they're interested in what's this energy all about. National Science Foundation, a 5-year project looking at hundreds of millions of galaxies, thousands of clusters, 4,000 or 5,000 supernova, looking at simultaneously galaxy probing dark energy clusters, supernova, the large clumping of galaxies, and gravitational lensing.
And when does that start?
They just installed it in the last few months, so it's supposed to, start right now. I mean, maybe a month or two away. They may have started last week. That's going to be that's at the 4-meter down in Chile. Now, as an ancillary to that, this is back to our 4-meter on Kitt Peak. There's a project called Big Boss. The reason they call it Big Boss is they've already doing BOSS. BOSS is a project being done at the Sloan Digital Sky Survey. Some may be aware of that at Apache Point, New Mexico. But this is Baryonic Oscillation Spectroscopic Study is what BOSS stands for. But basically, what they're going to be doing is they're going to be putting in a very powerful spectrograph that has 5,000 fibers, which means they can view 5,000 galaxies and 5,000 galactic spectra, or spectra plural, at the same time, okay? And whereas Blanco is looking at dark energy, this is going to be basically trying to get take dark matter. And again, it's going to have a lot of same coverage, overlap with pan-stars. But then it's going to have some areas that's going to complement pan-stars. They're going to be probably collaborating with each other. Looking at 20 million galaxy redshifts, it's got again number of U.S. institutions as well as China. There's China again, France, Korea, Spain, etc. Managed by Lawrence Berkeley National Lab, and then operated at Kitt Peak $100 million, 10 years. Okay, now we're going to leave Kitt Peak briefly. This is a picture of Kitt Peak. Remember the annual, did you get an eclipse here last year? We got about 80% coverage, 85% in Tucson. This is a photograph of the setting sun, Kitt Peak, from Mount Hopkins, about 50 miles away. And of course, whenever you have a setting sun, twilight in Arizona, what happens? Coyotes. They don't howl, they yip. So,
Still be kind of
pardon?
still be, like I said, my grandparents lived in
Oh, yes, you've heard the coyotes yip.
It's a little bit, it's hair raising.
Yeah, because you're sitting there and you hear, it's like these teenagers are outside making noise.
It's spookier than teenagers. It really
It really can be spooky, yeah. It's not just a howl. So this is Mount Hopkins. And MMT. In 1979, this saw first light as the multiple mirror telescope. It has 6 1.8 meter mirrors. These became equivalent to about a 4.5 meter telescope. And then in 2000, they had the technology, they replaced these multiple mirrors with one monolithic mirror, 6.5 meters. Fortunately, it was a monolithic mirror because they never changed the name. It's an MMT, but now it's monolithic mirror telescope, not multiple mirror telescope. Otherwise, people wouldn't know what they were talking about. So you can actually visit this site, too. You can take trips up there. Now, you can't drive your car, but you can go and take a tour. And then here it shows their adaptive optics. One thing interesting, this is in the Santa Rita Mountains, and they put out wildlife cameras in the wilderness, and University of Arizona and National Fish and Wildlife Service. And recently, they have caught a couple photographs. This is the same character. Anybody know what this is? Pardon? Jaguar. And these guys usually, you don't think of them. I mean, one time their range was in southern Arizona, but you think of them down. If you look at a book, it'll say into Mexico, but doesn't show anything near the U.S. But this is the Jaguar. It's the same one. And now this is this year. Just happened in October, November. A couple years ago, they had another one. So kind of interesting. Driving to work someday, and you see a Jaguar crossing the street. Fascinating thing about this. This is part of this Smithsonian, University of Arizona, Mount Hopkins conglomeration. But this is a gamma ray telescope. It's called Veritas, which is Latin for truth. Yeah. It sits at about 4,000 feet, and what this is, these are 4 12-meter Cherenkov telescopes. There's about 350 mirrors. Cherenkov telescopes are interesting. Gamma rays don't make it through the atmosphere. Okay. But what they figured out, and the guy that figured it out was Cherenkov, who was a Russian physicist. He got the Nobel Prize in Physics in 1958. He figured out that when the gamma rays hit the upper atmosphere, they basically cause a secondary radiation, which is a bright blue flash. And these telescopes pick up those flashes. So fascinating. Veritas, there's another picture of it. In what that stands for, it's going to be on the test, but I'll show you what it is. Very energetic radiation imaging telescope array system. And I read recently that the Germans are putting together a large array of gamma ray telescopes. Look like this. Yes?
Are they actually able to image based on the flashes that are in the sky, or are they just getting like a density or a fog of what the gamma ray?
I think what they try to do is they can try to get the location pretty well. And then they try to see if there's any optical signature that's left behind. So something that happens. Gamma ray, very energetic. When gamma rays go off, something big is happening. Whether it's a supernova, whether it's something very energetic. So they're trying to then identify through other like X-rays or optical if there's something there to figure out what caused that, supernova or whatever. That's probably not a very good answer to your question. They're imaging the location. I'm not too sure if they're imaging the actual gamma radiation itself. Yeah, that's a good question. You're kind of getting a shadow, perhaps, of what it is through that. That's a good question. That's a good Google. There's so much to Google. Okay, this looks like a small telescope. This is a huge building. This is the Large Binocular Telescope, Mount Graham, 10,000 feet. These things are huge. There's the size of this mirror. That is huge. To give you an idea, a couple ideas. And again, these things are so expensive. The 3 state universities in Arizona, a bunch of universities, Italy, Germany, they're involved in this consortia. some other universities, Ohio State. This is a diagram. This is the mirror itself. Here's a person. You can see how huge this structure is. Big, big structure. This is supposedly the largest telescope in the world on a single mount. So even though they're 8 meters, they're equivalent to it's equivalent to about a 12-meter telescope in total. They can be worked independently or they can be worked together. And this is, pardon? I had a question? Okay, now this is the Mirror Lab, the Stewart Observatory Mirror Lab, which happens to be University of Arizona underneath the football stadium. That's where they make these large mirrors. And what specifically they've worked on, this is the LSST, the Large Synoptic Survey Telescope. 8-meter mirror. Kind of interesting. This is what's good. This telescope is going to, let me show you where it's going to go first. There's 2 of them here. It's going to go down in Pachón, Sierra Pachón in Chile. It's going to look something like this. It's a survey telescope doing kind of the same thing that Pan-STARRS is doing. And what's interesting about this, it has this is the mirror here, 8.4 meters. The light hits this mirror, bounces to a secondary, down to a mirror that has been basically polished into this surface. So this tertiary mirror is actually in the telescope, polished into the telescope. And it effectively makes this only a 6.7 meter mirror. But I don't know of any other mirrors that have this multiple design. And this is Magellan. This is going to go in Las Campanas, which is 8,500 feet in Chile. These are 7 8-meter mirrors. And I show 8.4. And I show this because the Mirror Lab here has worked on about 18 mirrors over the past 20 years. It's still working on this. It's working on the 3rd Magellan mirrors, all the big mirrors. Whether it's the WIYN mirror in Kitt Peak, the one you saw at Mount Hopkins, a 6.5, these mirrors, these are all being basically put together, polished, cast at the University of Arizona. Okay, we're getting close to the end here. I wanted to show you this. Everyone know what this is? This is a 30-meter telescope scheduled to go into Mauna Kea. We're back to Hawaii. You can see the size of this. Look at the size of these parking. They should have put a car there. Look at those. I know Hawaii has small parking lots, but it's still, or parking spaces, but still a big telescope. And Caltech, University of California, again, see China's always in there. China, Japan, India. It has almost 500, 1.4 meter. 1.4 meters is about 5 feet. 500 meters. 500 mirrors. This is about this size. Yeah, absolutely, yeah. Because we can only really make 8.4 is about the maximum. One reason is more than 8.4, you can't transport it on a road. You can't put it on a rail car. You can't get it through tunnels. So 8.4 is kind of the limit for a monolithic mirror. Anything bigger than that, they're going to be segmented. Yes.
What's the new solar telescope in Haleakalā going to accomplish that these other solar telescopes aren't able to do?
Well, the other ones are only 1.4, 1.6 meters. This one is going to be bigger mirror. It's going to be allowed better resolution of the sun. It's going to be able to look at the granulation on the sun, identify the magnetic fields. You know, when we have sunspots, those are basically magnetic storms. So it's going to give us more characterization to understand the sun and how the sun's operating, what's happening.
Very much finer angle.
Yeah, the resolution, you're going to see the granulation is going to be much clearer, larger. Yeah. Anyone know where we're going now, real quick? We're going back to South America. Anyone know what this is? It's ALMA, which stands for Atacama Large Millimeter / Submillimeter Array. Almost done, 2013. 50 12-meter telescope meter antennas over 16,000 feet. And the EELT, the European Extremely Large Telescope, almost 40 meters in diameter. Probably not. or will it stay funded if it is? 2022, first light, that's 10 years away. Sierra Armazonas at 10,000 feet, 800 mirrors, 1.5 meter hexagons. This, by the way, Armazonas is the other site they were looking at for the Advanced Technology Solar Telescope. So Haleakalā won, but worst comes to worst, I guess they could have put it here because that's about the same elevation. Okay, we're getting real close to the end. This is kind of a cool picture. I've seen these where you see the shadow of the mountain on the clouds. I've seen one of Mauna Kea. JD was saying there's one of Haleakalā. And what I want to talk about here is divestiture, because last year the National Science Foundation had a committee to look at budget issues. Everyone's got budget issues. They recommended, this committee, that NOAO divest itself of the 4 meter, the 2.1, and their share of the WIYN telescope on Kitt Peak. So the National Science Foundation hasn't approved that yet, but they could. So what Kitt Peak is doing now, they're trying to find people, other partners. A divestiture just means we, the National Science Foundation, don't want to pay for it anymore. But they're looking for partners. I've seen an advertisement that WIYN is sending out, looking for someone to partner with them on that Wisconsin, Indiana, Yale telescope that's a brand new telescope. That, by the way, has the second largest camera in the world, a 1 gigabyte camera. So they're looking for partners. They're even looking for partners that would take the 4 meter as well as the 3.5 and make them kind of one organization, one consortium. So anyway, it's the people who work there are kind of wondering what's going to happen to their jobs, because divestiture may or may not occur. If it does occur, they may or may not get partners to basically step up and share in the cost of those telescopes. So that's kind of the cloud over this. Big Boss, which is going to be $100 million, maybe the fact that the Department of Energy wants to fund this for the dark matter study, that could actually save that telescope, because that's going to basically be a 10-year project that's going to basically put a kind of a facelift on that 4 meter telescope. So this is about the last. Anyone know what this is? Over Arizona? March 2001. This aurora. It was this is a 30-second photograph, and it happened again at solar maximum, March 2001. And understand, the guy that took this, there's some striations here, so he saw that it wasn't just static. There was actually some movement of that aurora. That's pretty far south for an aurora, but that's what happens at solar max. Okay, now, one thing I want to show you, and then we're all done, and this is a 2-minute video that I think is awesome because it shows you the stellar scales. So let me just play this, if it works. Here's the Earth. Earth is almost 8,000 miles in diameter. Get rid of the advertisements. Every time I play it, it's a different advertisement. I wonder why that is. Compared to the Sun. Now, the Sun is, 870,000 miles in diameter, so you could put about 110 Earths across the diameter. If you could open the Sun up, you could put 1 million Earths inside the Sun. The Sun's a pretty big star. I mean, it's kind of average, but I think it's a little bit bigger than average. Eight light minutes away. And now we're going to see it compared to Rigel, which is a blue giant. If you go out tonight and look towards the east, look up at Orion. If you look at it, it's going to be that bright star kind of on the right side, because Orion's kind of coming up on his back or his front. So it's that bright blue star. It's a huge, Rigel's a huge star, very big blue giant star. But a couple years ago, they found what so far is the largest star they've been able to identify. It's called VY Canis Majoris. It's in Canis Major. And you're going to see, now you remember where the Earth is? Remember where the Earth is? Somewhere close to that huge sun that's disappeared. Here's VY Canis Majoris. They're not positive. They think that this thing would go out beyond the orbit of Jupiter if it was in the middle of our solar system. And you can't even see the sun anymore, let alone the Earth. So it's kind of an awesome little video in terms of the scale of the universe. And that basically is it. Any questions? Everybody stayed awake. Everyone stayed awake. No one fell asleep. Except that one person in the fourth. No, yes, go ahead. About 145 feet is my understanding.
If you could repeat the questions.
The question is, how high is the telescope building on Haleakalā going to be? 145, roughly? I mean, maybe 143. I think it was 144, 445. So what you saw was the one on Kitt Peak is 185. So if you basically go down about a third of that, not quite a half, maybe a third or a quarter of that, that's how high it'll be. So it's going to be a good size cell. It's going to be a good size building. Yes.
What is the status of the James Webb Telescope?
Okay. Well, yeah, it was close. It was close last year and the year before. They were really worried. Originally, it was going to be $1 billion, and then it increased, and then it was right now it's $8.5 billion. So it got close to being canceled. So if it was the increase in cost, which it still could, because it's a few years away, they could still cancel it. But yeah, not cheap. Yeah, 8.5 billion. I mean, the Hubble telescope. What was that? That was about $1 billion, I think.
Why is it so much?
Why so much?
Yeah.
Well, first of all, the technology involved. You know, you're trying to build this. The size of it. Hubble is only 2.4 meters. Now, Hubble's not very big. 2.4 meters is what, about 9 feet, get roughly 9 feet. So this is going to be 6.5 meters. It's going to have has to have those hexagons because they have to fold it up to get it in the rocket, and then it's got a large, basically a shield to shield the sun. It's going to be in orbit at L2, which is a Lagrange point, which is a gravitationally stable point, 1 million miles away from the Earth, away from the sun, and the Earth. I mean, the not the sun side of the Earth, but going out from the Earth 1 million miles away. So, and the technology is going to be such, they're trying to make it good. So things are expensive. Yeah. Any other questions?
Maybe you go back to that 2-minute video and then show a Hawaiian parking lot.
Like a nanometer, right? Okay, any other questions at all? Going once, going twice? Hey, thank you all. Hope you enjoyed. Sorry I went over. It was their fault, not mine.
I know.